two systems, and there are two systems. They call it dark lights and dark and bright lights. Let me see what we say lights. So we have one generator here, G1, and we have another generator here, G2. They put three bulbs here. This is the A1, this is the A2. This is the B1, this is the B2. This is C1, this is C2. They connect one bulb here, and they connect another bulb here. Oh no. And they connect the third one here. Right? And these two are going to connect together. Let's see here. This is the A, we're going to go here. E, we're going to go here. And C. Right? They are not connected, We have a breaker here, a three-phase breaker. So look at here. If the system, you are in the frequency, magnitude, everything is checked, right? And we have put one bulb here. I have put one bulb here, right? Another bulb here. And another bulb here. Let's see. Right? Huh? Oh, yeah. It's a little like, So, usually it's like this. Before this waveform, you cannot, match the frequency exactly to be the same. It's very, very difficult,
Just connecting them together to light bulbs, is that right?
Yeah, these are no. You see, the real circuit is here, the hardware is here. But this is something, you look at on the scope, you have this three-phase here, you have this three-phase here. But this is not in reality. You cannot have that one and the bulb here. This is this circuit, I'm drawing it here. You cannot match the frequency perfect. It's extremely difficult, As soon as you have a small difference between the generator number 1 and number 2, can you tell me what happens? If you put these two into a scope, this one and this one into a scope, you are measuring, and let's say this one is fixed. This is, for example, this is 60 hertz, right? And this is, for example, 60.01 hertz. No, forget the light bulb. For now, we don't have it. We have a three-phase system. I'm watching this one on the scope. I connect this one here, and I trigger on this one. This one is fixed on the scope, right? If this one is not moving around, I'm triggering on this one. I put another set here, another generator here, but the frequency of this one is not exactly 60. It's 60.01 or 59 point, I don't know, 0.9, something like that. What do you understand on the scope? No interference. See, there is no problem here. I'm looking at two sources, right? Just forget the three-phase. Just say I have one single-phase source, right, 60 hertz. I have another one. This is 60, and this is, for example, 61 hertz, right? Try this one. We don't have another frequency here. If this one is fixed, this one is going to start either move this way or this way. You know what I'm saying? So it's not going to fix, but the frequency, the speed of these two are different, right? It's going to move with the difference of the speed of with 1 hertz. It's going to move that way or this way. Because what I'm putting here, you get confused. So, see, this is the best place. See, this voltage matches this voltage, right? So how much this bulb is going to be dark, right? Because how much voltage is saying? 0. But this is a perfect time when both of them, they're lined up exactly, right? But you connect it and you start to look at this bulb. You see, they become, unfortunately we don't have this test here. Don't close the breaker. You look at it, this bulb, they're going to become dark, become very bright, and again become dark, bright, right? Because this guy is passing, right? When we are here, dark, right? Let's say this one come here. Worst case, right? This is minimum, this is maximum, right? It becomes very bright, right? So basically by looking at these lights, you can see, okay, how much is the difference, right? If it's dark, means it's a good time to close the switch, right? Why is a good time? Because this one is the same voltage with this one is the same voltage with this one, and this one is the same voltage with this one, right? All of them, they are in the same phase, right? And as soon as you close this one, these two, they will lock together. They cannot go with a different speed anymore. You know, but they're connected together after that point. Both of them they're going to go 60 hertz or 59.9. The one is stronger, is going to run the system. And the other one has to follow this one. But before they are connected together, this guy can go either faster or slower, right? So basically, you look at the bulb, when the bulb is dark, means they have the same voltage, right? There is some error, you know, because if you look at the bulb, I mean, the 5 volt is still going to be dark, right? So you look at it, and when you see all the bulbs are dark, is it close the switch? Is the time to close the switch, right? All of them are in the same phase, right? Is it clear here? To make it a little bit better, to make this method a little bit better, I'm going to do this. Connect this one to C, and this one to B. Let me see. No, this one should go through this. Yeah. No, let me see. What are those? I connect this one to C. This one should be connected to B. And A to A. A to A, B1 to C2, and C1 to B2. Can you tell me what's going to happen?
It's going to be bright when they're in phase.
Huh?
It's going to be bright when they're in phase.
2 of them are going to be bright.
And the other one's dark.
Dark. So basically a little bit more accuracy when you're, this is off, these two, they are bright. You know, this one was a little bit easier to do. We have done this test in the lab. You know, unfortunately we don't have this one. You look at this light, they call it dark and light bulb, you know, or bright bulb, you know. So basically, you look at this one, 2 of them, they should be very bright. 1 of them should be dark, right? So you look at it by this, and you can close the switch. But in the power plant, there is not somebody over there to do this one. Look at bulbs, you know. But still, they have bulbs. You can see, but it's not for this kind of thing. Maybe kind of symbolic. They will measure this one. They will measure this voltage. They have it could be a very, very simple circuit. You have one comparator to compare these 2 voltages. You compare this one with these 2 voltages, and this when you give it a kind of, you know, like for example, 5 volt, you know, error, right? Not error, band. You know, say if this one is, if the difference is less than 5, if the difference is less than 5, add all of them together. When all of them, the difference is less than 5, it's going to give you one signal for the breaker, right? I'm saying it will be a very simple circuit to design it. You know, you need a 3 voltage sensor to measure each voltage, right? Actually, more than 3. You need a 6 sensors because you need, or maybe you need 4 because you can measure VAC and VAB and VAC and VAB here. You know, you can do it that way. But you measure voltage here, VA. For example, you measure VA1 and VA2. You give it to a comparator, right? 1 signal, right? And here you compare it again with a 0. And if this one is more than, not this thing, you know, it has to be, you have to have another part circuit here to see if this one is less than 5, give me another signal, right? Let me see if it's less than 5, I want to be high. Less than 5. So basically, with this one, less than 5, if I connect this one to 5, right? If I'm more than 5, this one is 0, yeah, let's circle like this, right? If I'm more than 5, this one is going to be 0. If I'm less than 5, this one is going to be high, right? You put 3 of these circuits, right? You put them here, put in an AND gate, this is the signal to go to a circuit breaker, right? If all of them they are 1, so this one is going to be 1, so it means the condition is okay just to close that break. Right.
It's like AND gate, not OR gate.
No, OR no, because OR said if one of them. Oh, this is OR, sorry, good. And, yeah, and this is good and. Yeah. And when all of them they are 1, you can close it. This is a very simple thing. They call it synchroscope. If you go to the power plant, you will see it. But nowadays, with power electronics, we'll talk about it a little bit in power electronics too. They call it PLL. Phase lock loop. They call it PLL because all this solar systems installed at home, they're single phase system, right? They're connected to the utility grid, right? The PLL is a piece of software. Still, it does measure the voltage of the grid, and is going to go find the phase of the grid. We'll talk about this one in power electronics too. Not maybe PLL itself, but the phase I'm talking about. It's going to go find for example, this is the grid voltage. It's going to give you a signal like 0, 2, 5, right? It's going to be a sawtooth signal like this. Right? It's going to give me this signal. Basically, this signal is giving me the phase of the grid, right? I can use this signal to generate another voltage with the same phase exactly as this one, right? If I use this one to generate another AC signal, I'm going to have this one in the same phase, right? I calculated the phase of this voltage. Next, I use this phase to generate a new voltage, which is my inverter, right? So now I know these two are in the same phase. I can connect it together. They call it PLL, phase lock loop. Yep.
And most power electronics can be fast enough that you don't have to worry about like time delays.
No, usually give you with the product you have in the company, usually the system is like this. PLL, the control system, if you look at the system, there is a hardware here, it could be inverter, whatever, and there is a control board here. This control board is going to measure current, measure voltage, whatever, all those kind of things. And there is a breaker here. There is a breaker usually here. Let's say this is your grid, right? This is going to measure on the grid side, which after closing this switch is going to be inverter side also, right? But you need to measure this one before this switch is closed. You measure this voltage, you give it to your PLL, PLL generate that signal, right? And when you get an okay signal from your PLL, because PLL needs to lock, it needs time to lock. When you get an okay signal from your PLL, you say, hey, I found the phase, I know what's the phase now. It's going to go generate a voltage here, which is going to be the same phase with this one. And you say, now close. As soon as you get the okay from your PLL to say, hey, I'm good, I like the phase, you can close that switch. I'll give you the equation for PLL, those things. It's not part of the course, just to mention it. But for those guys, those people, they are interested. There is a very good IEEE paper. They modeled this one. I used it 2004, when I was working on a product in American Electric Power. And we built it. It worked perfect. It worked perfect. It worked with phase system. But if you want to just type PLL, on the Google, you're going to find nowadays you can find a lot of documents. This is the way they use new days with the inverter, to lock the inverter as a new source to the grid. But old system was a synchroscope. They call it synchroscope. And if you go to the power plant, still you see the synchroscope, and it shows you when you can, they have a manual and they have automatic to connect the generator to the system. So we talked about this one a little bit, how they parallel this system, what conditions do we need to have to parallel the system. Now let's get to the equation a little bit, what happens when we are going to parallel two systems. They were not available, like PLL and those kind of things. You go back, so power plant has been there for more than 100 years. Now you go to the TI, you find a small chip. it calculates, even they have a phase lock chip, you can buy that one and just put it there and give you the phase. You know, you don't have to write any code yourself. You know, but you go back 50 years ago, there was not such a thing like that. The microcontroller was not that. They were not that fast. They were expensive. You know, but now they're definitely becoming very small, very cheap, very reliable, and very accurate. You know, things are changing. You know, if they want to build today a power plant, I don't think today anybody is going to use Synchronous anymore. You know, they go come over a very, very simple microcontroller. It will check everything for you, frequencies, voltage sequence, everything. It's simple things. You can check everything and get very, very accurate measurement and for operating the system. But now let's look at the parallel transform generator. Did you talk about parallel transformer in the power system course or not? Yeah. So remember one thing about the circulation current, about the power, and we talked about the ratio of the voltage and those kind of things should be the same. Kind of similar things here, a little bit different. We have two generators, G1, and we have a G2, and we have a load. Is a three-phase load, these are generators, right? So let's put the circuit together for this generator. This is a symbolic drawing of this system. This generator is going to be EAF 1, right? RA1, JXS1, and right? And I draw only one phase of the system, right? I draw, for example, phase A of the system. Initially, when, let's say the load, this one is not there. Let's say this one is not coming. Let's say this one, call it S1, S2, S2. When we close S1 and S2, they're closed, right? And S3 is still open. S3 is still open. So we are going to have a current here, right? We're going to talk about this current first. If S3 is not there, is it good to have current or not? I see. Why is it not good to have current? Huh? No, I know. We will talk about the reasons why it's going to be there. But I'm saying why it's not good to have it here. Power loss. See, this is a no load condition, right? This is the load, right? If this switch is open, there is no load, right? But if there is a current here, just look at this one. Forget this one, right? If it's a no load, there is no current, right? If there is a load, there is some current going this way. Or again, look at this one. If there is no load, no current. If there is a load, there is current, right? Now it's a no load condition. So what the heck is this current, right? It's like a fake load, right, in the system. So we call it circulation current. IC is a circulation current. And how much is IC? IC is equal to EAF1. These are phasor. Let's put it this way. Minus EAF2 or the bigger the IC, the worse mismatch. We parallel two generators, which they are not very good. Think about it, as I'll give you an example. We have a fast runner or a slow runner. We tie these two together, right? And they start to run together. So what's going to happen? The guy is